Welcome to yet another webinar on steel structure design in ETABS. So our focus is on PEB shed as per IS 800-2007. Let me introduce myself. My name is Unbraced Bhaduri from CSI India. So what are the objectives of this webinar? So we will be continuing from where we left off the previous webinar on the 6th of September 2025. So we are basically targeting users who use ETABS for steel design, the design steps and its integration within the software will be discussed. So users who have been using ETABS, they all know that the default design combinations are available within the software, which is as per IS 800-2007. So the requirements. Now coming to some of the prerequisites for the design. So design factors are generally captured from the model, like the unbraced length ratios and the effective length factors. However, the designer should review them before proceeding with the design. And they can also overwrite some of these factors by using the design overrides available in the design menu under override frame design procedure. And once they are overwritten, the overrides persist through the entire modeling cycle. So this is a flow chart for the strength design as per IS 800. And these same steps are integrated within the software. So the first step, I'll just briefly explain all of them. The first step is the design prerequisites like the model geometry, loads, materials, sections, etc. So then we run the analysis and design once the first step is completed. Now we get into the main design workflow. The program carries out the section classification as per table 2 of the IS code. It then evaluates the unbraced length ratios and the effective length factors. So after that, the user has to review them, basically the unbraced length ratios, and then he or she can manually override them if required. After that, the program calculates the tension capacity as per section 6. It calculates the slenderness ratios for both sway as well as a non-sway case. And then it reviews whether the frame is a sway or non-sway as per clause 4.1.2. And the appropriate slenderness ratios are selected. The capital K factors or the effective length factors for beams and braces are generally kept as 1. And then the program computes the compressive strength as per section 7. After that, it checks the shear capacity, and if the element has high shear condition, it then modifies the bending moment capacity as per section 9.2, or else it will just compute the bending moment capacity as per section 8.1, and then finally it will check for the bending and combined forces as per section 9 and report the strength demand capacity. depending on the uh, depth to thickness ratio and width to thickness ratio of webs and flanges respectively. It will also use the axial force that is generated in the member for checking the section classifications. So here are the screenshots from the ETABS design manual, which is as per table 2 of IS 800. Let's quickly jump to an example model where we will verify these steps one by one. So this is the model of the industrial shed that we had discussed in the previous webinar. Okay, so I will just run the analysis. Now, before running the design, I will go to the view revise preferences. Here, we will turn off the consider P delta done so that the program gets the opportunity to calculate the effective length factors. So once the design is run, from the display design info, you can check the maximum ratio colors or the PM ratio values, which are nothing but the demand capacity ratio that we had discussed in the flowchart. So coming back to the presentation, so we will be verifying the section classification for column C16, which is marked here with the red colored arrow. So the program classifies the column section as class 1, and on manual calculations in an Excel sheet, we get this same classification that the program does. So the program will check the classification for the web member as well as the flange. So coming back to the model, we'll select the C16 member. Okay, so this is the C16 member. Okay, so on right clicking this, you will get the interactive steel design and review form. Now, since the frame section was defined as an auto select, you will get multiple. You will get a list of multiple sections, and the individual demand capacity ratios will be reported. So program will report the member with the highest demand capacity ratio, that is 0.893. Okay, we'll now shift the focus to the report. So in the report, the program, it classifies the section as class 1. Okay, let us also see the Excel sheet where the calculation was done. Okay, so the axial force on the member is minus 58.5859, which is taken from the report. And the program does the calculation of the R1 factor, and it calculates the limit for the slenderness ratio for the section classification, and it classifies it as a class 1 section. Okay, the next step is the unbraced length ratio. So the program, it identifies the length between the two bracing points of a member, and it divides that by the overall member length to report the unbraced length ratio. So if the bracing points are modeled within the program, then it will identify the bracing points. Otherwise, the user has to provide overrides or use the lateral bracing option. The next step that the program takes is the capital K factor calculation as per Annexure D. So the program internally runs the check on the structure as per clause 4.1.2 and classifies it as a sway or a non-sway frame. However, it will calculate both the capital K factors and then finally take up the appropriate capital K factor for the structure. So here we have done the capital K factor verification for the C16 column itself. So these are the factors that the program reports. For both the sway and non-sway case. So for the non-sway, it is reported as major braced, and for sway, it is just reported as major ZZ. So program also reports the capital K factor for lateral torsional buckling, which is nothing but the K factor for the minor sway case. So similarly, we have calculated the capital K factors or the effective length factors from the Excel sheets, and you can see the capital K factors tally with the program calculated capital K factors. So coming back to the model, so this is where the program reports the basic factors just below the PMM demand capacity ratio. Okay, let me just briefly guide you through what it all reports. So in the first page, you have the element details, where the critical combination is reported and the location where the stress check is carried out. It does the classification that we have seen in the previous slide. Okay, it reports the material properties, the section properties, the critical stresses, and next it reports the PMM demand capacity ratio. We'll come to this in the later slides. Okay, so basic factors are reported here, which are the capital K factors and the unbraced length ratio, or the capital L factor, which is used in turn for the slenderness ratio calculation. Okay, next are the CM and C1 factors. So these factors are also calculated within the program. Now, it depends whether the frame is a sway or a non-sway type, and the appropriate CM factors are calculated from the IS code table number 18. And also the amplification factors for the second order effects are also captured. Next is for the, after these factors are calculated, the program then moves into the design. So the first step is it will design for tension. So as per IS code, the design tension tensile strength is the minimum of the yielding of cross section and the rupture of the net critical section. So the user has the provision of providing the net area or the net cross sectional area by using the overrides. The program will then calculate the rupture of the net critical section as well. So moving on to the next slide, we have performed the similar tensile strength verification for the C16 column. So the design capacity, that is TD, is reported as 1224.7814, and we have also verified that manually by the help of a spreadsheet. Okay, the program also reports the TDN, which is the net, which is the rupture of the net cross section. Now, in this case, we have not provided a reduction in the net tensile area, and hence this is naturally higher than the gross yielding. Okay, let me also show the Excel sheet. Okay, so a simple formula in the Excel sheet will calculate the tensile strength of the member. So this is the gross and this is the net for the gross cross section and the net cross section. Next step is the design for compression. So the design compressive strength is calculated for both the buckling as well as for the buckling limit state as well as for the torsional or flexural torsional buckling. So this particular mode of design compressive strength calculation is not available in the IS code as of now. The users can accept these values for the or provide additional overrides in the program. So we have again done the compression strength verification for column C16. So the axial force design, the program reports the PZ as 1224.78 and PD as 764. So this is basically for the major and the minor axis buckling. And you can also verify that manually in the spreadsheet. Next step is the design for flexure. So the flexural strength is evaluated for a lateral supported case, a laterally unsupported case, and the uh, moment capacity is modified in the case of a high shear condition. So coming to the flexural strength verification for column C16. So the program reports the yield capacity, MDV capacity, MND, and the MDLTB, which comes from the lateral torsional buckling. So these values again can be verified from the Excel sheet where the MDLTB values are calculated. So program will also calculate the MCR values or the critical bending moment for lateral torsional buckling, and you will also be able to verify the MDLTBs that the program is calculating. Okay, so MDZ is for the uh, laterally supported condition, and MNDZ or the MND is the modified moment capacity in the case of high shear. So you will be noticing in the slide next to this that the stress ratio for shear force is less than 0.6. Hence, the MND capacity will be same as the previous one. So there will be no modification of the MND values. Okay, so we have done the verification of the demand capacity of the moment capacity in the spreadsheet. Okay, now coming back to the model. Okay, so the basic factors are reported here. Just below that, we have the axial force design, where the program will report the tensile capacity, as well as the compression capacities. So you can see here the A net to A gross ratio is 1. Okay, so there has been no reduction in the gross area of the cross section. Next, the program calculates the design parameters for the axial design. Okay, it will calculate the Euler stress or the FCC values, and then the non-dimensional slenderness factors. And finally, it will report the FCD values. So the appropriate FCD values will be used for calculating the compressive strength of the member, depending on the sway or non-sway type of the frame. Okay, next is the moment capacity that is being reported by the program. So you have the uh, demand on the structure that is being reported. Okay, and then you have the capacities. Then we have the, for the minor axis as well, the program computes the capacities. And then the factors for the uh, lateral torsional buckling, which are used for the MCR and FBD calculation. Those are reported here under the factors table. Next is the design for shear. So the program calculates the shear strength of this section, as well as it will evaluate the shear buckling of the web member, provided the D by TW ratio is inadequate. So going on to the shear strength verification for column C16. So we have the capacity of the member, which is calculated using this particular formula that is given in the IS code. Okay, so our yield stress is 345 MPa that has been used in the model. So the demand capacity ratio for the shear forces, they have also been evaluated manually in the spreadsheet. So these also tally with the program calculated DCRs. The next step is the combined checks for the members. So in a real life structure, members do not attract only one type of forces or moments. It is more of a combination of axial forces, shears, and bending moments, along with torsion. And the program is, and the program, as per the clauses of the IS 800 code, will treat the members in such a manner. So whatever we have discussed up till now, the same procedure will be followed for a beam section as well, where some kind of axial forces are also generated, with one exception, that a serviceability check for the beam sections will be inbuilt within the program. Okay, so for the combined checks, the program checks the stresses in the member in as per section 9.3 of the IS code. So all these equations are integrated within the program. So program does a check for these as well. For example, this equation, section 9.3.1, if you closely look into the design report, you will find them here. Okay, so alpha 1 and alpha 2 is also reported along with the individual ratios for my dy and mz dz. So if this is critical, the program will report this particular ratio. And finally, it will check for equation 9.3.2. So the demand capacity ratio for this particular member is being reported as per 9.3.2.2a. So there are two sets of equations for the torsional buckling check of a column. Okay, so program will check the section strength as well as the overall member strength against buckling. Okay, so for the same C16 column, we have done the verification of the demand capacity ratio that is being reported. So in this report, the program uh, reports the numerical values in this fashion. The demand capacity ratio is a summation of the axial ratio. The first term is the axial ratio. Second term is the major ratio. And the third term is the minor ratio. So this equation, the program basically reports. The program will basically print the formula that is given in the IS code directly. However, while reporting the values, this is the format in which it is reported. Okay, so for the verification purpose, we have evaluated the ratios both for equation A as well as B. So this nomenclature, 9.3.2, 2.2A or B is there in the IS code. So we have calculated the individual ratios for the different components for equation A as well as equation B. And we have summed them up here. You can see these ratios, they more or less tally with the demand capacity ratio being reported by the program. So coming back to the Excel sheet. Okay, so here we have basically calculated the individual ratios and use the appropriate multiplication factors as per the IS code. So these factors are also reported by the program. So you can see here these factors, they are being reported by the program that is being used in the evaluation of the demand capacity ratio. Next, we are going into the verification of the deflection that is being reported by the program. So we are verifying it for the member shown in blue. So this is the B148 element. Okay, so let's come back to the model. You can see here in the design details for the column section, there are no deflection summary or deflection envelopes. So we'll select the B148 beam. So right click on that will open up the interactive steel design and review form. So you have the strength checks here as well as the deflection checks. So program automatically creates, when you're using the default design combinations, it creates the uh, serviceability combinations, which are named as D, and for strength, it is S. So at a 2.5 meters location, there is a deflection of 12.203, and the allowable is 41.667. So you have a demand capacity ratio of 0.293. Can open up the report. So in the report here, you can see the format of reporting is same like that of the column. In fact, the design procedure is same for the strength. Now we'll go to the deflection summary, which is specifically reported for beams. Okay, you can see here, this is 12.2, the deflection. So the D1 load combination basically has the dead load only. Okay, you can check the diagrams as well. So from the load combinations, you can select the D1 load combination. So it is reporting a deflection of 12.203 at the midspan. Okay, for checking the equivalent load on the member, you can turn on the load case for dead. So since D1 consists only of the dead load case, okay, you can see this is the equivalent UDL on the member having an intensity of 0.210 kilonewton per meter. Okay, so this is the deflection that is being reported, right? And we have also done the deflection check. So we have taken the UDL on the beam from the equivalent load on that particular beam, and we have used the formula for arriving at the deflection, so which is 12.31, and the program reported is 12.2. So basic difference here is the program calculates the deflection using the M by EI curves, which is parabolic in nature. Okay. So a few more points that I will discuss for the users. So in this 2023, in this ETABS 23 version, we have the interactive steel design form. So which is a little different from the earlier reports that were generated. Okay, so here basically it will report the demand capacity ratio for all the members that are available within the auto select list. Okay, you can turn on the alternatives if there are any other members that are not being reported, they will be displayed here. For example, if I just turn on this form, okay, so you can see there is a member ISMB 200 which has a demand capacity ratio greater than 1. So that itself will be hidden. Okay, you can check the reports of the individual members by going to the report, and you can investigate the reason for the failure. So here basically, okay, so for selecting the members that have failed, you can go from the drop down menu. You can select verify all members passed. So program will report that 12 frames have failed the capacity check. You can select them and go to show selected objects only. So here you will get the members that have failed in the PMM ratios. Okay, there can be some other failures as well. For example, the slenderness ratios being exceeded. So you can check that by going to the display show tables, steel frame design output. You can turn on the steel frame design summary. Right. So you can check for the members individually. For example, these tables are customizable. You can select the column and the status. You can see the warning messages. Okay, so here from this list, you can see the KL by R ratios. And see the warning messages. So these tables can also be exported to Excel files from where you can view them in the Excel file. And you can also use the unique names that are being reported here for the members where the KL by R ratios are being exceeded. And you can select those members and check the issues in that particular member. For example, 231. So one frame is selected. You can right click on this and you can see here in the warning, the KL by R ratio is greater than 180. So program default by default will report the KL by R ratio greater than 180 for beams as well as columns. That's all. Thank you. Now we can open up the session for discussions. Okay, there are no queries. Okay, in the Q&A. All right. Okay, the wind load applications have already been discussed in the previous webinar on September 6, 2025. You can refer to that video. Yes, for bracing members, when there is only tension in the bracing, the slenderness limit of 400 is taken up by the program. However, for 250 slenderness ratio, if you read the clause carefully, the the IS code tells that the deformation of the such a member should not adversely affect the stress in any other part of the structure. So this involves a nonlinear analysis. Hence, the program reports for any general section as 180. So it is the engineer's discretion that has to be used in that case. So LTB slenderness ratio, it is already checked by the program. So torsional checks are not available in the IS code. However, the program does the torsional check. Cold form Z purlin, it is the design is not available in ETABS. However, you can analyze the structure. Connection design is available, but as per AISC, however, you can extract the forces from the tables for doing the IS 800 design. Okay, tapered columns and rafters, it's possible through non-prismatic sections, but how it will be a topic for another discussion. We can have such kind of a uh, tapering of sections in ETABS. Okay, the process of extraction of forces for connection design, we'll discuss that later. And some of the questions are repetitive. Okay, beam column joint design. This is done for a special moment frame. So in this discussion, we have considered an ordinary moment frame. The program does the beam column joint design, as well as the special seismic checks are also performed. Okay, so in the case of purlins, where if you're using sag rods, you can provide overrides for the minor direction as well. Yes, section 12, the program does the design for section 12 as well. Yes, lateral torsional buckling for tension member, it can be overwritten. Yes, you can also model uh, the column without the girt members as well. So for deflection of a frame, uh, you'll have to check the deformed shape as well as you can check from the tables. Yes, the recording will be available in the website as well as on YouTube, and the materials will be available. Yes, for the frame deflection, like I just said, you have to check from the deformed shape or use the tables. Okay, thank you for joining in. I think I have answered most of the questions.